our video, and today we're going to be looking at the limit convergence test, and we are also going to be looking at alternate sequences, alternate series tests. So those three things today. So first of all, I want to look at the limit convergence test. So what it says is if you have a sequence AN and BN, and they each are a series. So the series of AN, the series of BN. Let me just get this out of here really quick. So if the limit of the sequence AN over BN is equal to C, which is larger than zero. So if it's not zero, like if AN over BN and the limit of that to infinity is equal to something other than zero, then the series of AN and BN have to be both divergent or both convergent. So let me say that again. If the limit of the function of the sequences of AN over BN and the n to infinity, the limit of that is equal to something other than zero, that means that the series of AN and BN must be both either divergent or convergent. Both of them are the same. So let's do a quick example, right? So what we have is an example here, the sum of 2n squared plus 5 over the root of n to the 5 plus 1. So again, let's try to think. We want to find some other equation that we can do 1 over, or like, not 1 over, but we obviously want something in this form. Remember, it's all about that kind of like 1 over x to the p, and then p being less than 1, p being less than or equal to 1, that would be divergent. So it's usually around that. And we also want to look at what happens as n gets really big. So as n gets really big, we can really think that's, honestly, it's just the same as this, n squared over n to the 5 over 2. And then that would simplify down to 1 over n root of n. So now what you do is you take the limit convergence test of 1 over root of n over this, and then so you can do some manipulation, and then we can do some funky tricks where like we multiply it by 1 technically, but it's like a special form of 1, and then you do, and these cancel out. So you see here, let me just show you. So you do 1 over n root n over the original 1, simplify it, we get down to here, we multiply by 1 over n to the 5 over 2. What that is if you can imagine it, it's basically multiplying root of 1 of n over 5 like this. And so you multiply 1 over n over 5 into the square root there. What you end up with is n over 5 over n over 5, which is just equal to 1 plus 1 over n to the 5. And then you have this here right here. So you do n to the 5 over 2. That's going to be just 2 because then the n 5 over 2 cancels. And then this. And as n gets to infinity, these things go to 0. And what you end up with is the root of 1 over 2, which is just 1 over 2. And so the limit of these ones are equal to 1 over 2, which is not 0, and so it's larger than 0. And so we know that that 1 over root n and 2n squared plus 5 over root of n5 plus 1 must be either divergent or convergent. Both of them are the same. And we know for sure that 1 over root of n is divergent because we know that 1 over x to the power of p, where p is less than or equal to 1, that is going to be divergent. And so if 1 over root n is divergent, then 2n squared plus 5 over root of n to the 5 plus 1 must also be divergent through the limit comparison test. So that's one of the tests we learned today. And I'm going to move on to alternating sequences. So an alternating sequence is a series in the form, or I guess it's a series. Alternating series are in the form of the sum to infinity of minus 1 to the n of some random sequence bn, or it could be minus 1 to the power of n minus 1. So it could start with 1, or it could start with minus 1, depends. So sometimes it could be like 1 minus 1, 1 minus 1. It could also be minus 1, 1, minus 1, 1. It could also be something like this, where you have cos n pi, and so what that's going to end up with like this, right? So n equals 1, cos of pi is minus 1, right? Minus 1, cos of 2 pi is 1, cos of n 3 pi is minus 1. So that's how that works. And an alternating series test tells us that suppose you have an alternating series of this form, what you want to be looking at is bn, right? And if bn, the limit to infinity is equal to 0, and bn plus 1 is less than bn, which just means that if it's 1 and 1 over half, then 1 over 3, 1 over 3, minus 1, 1 over half like this, minus like this. If 1 is larger than 1 over 2, and then that's larger than 1 over 3, basically means it's decreasing, right? It's a decreasing series. And we're going to show how that works. So basically, first is if the limit to infinity of the sequence is 0, and then second, if it's a decreasing series. decreasing sequence. So let's look at an example. We have something here, right? The sum to infinity of -1 to the n minus 1 over n. And we can write that as -1 n minus 1 times 1 over n. So we know that Bn is equal to 1 over n. And it's going to look something like this. So we check the limit of infinity. So limit of 1 over n, that's going to be 0. And we check if it's going to be decreasing sequence. And 1 over n plus 1, that's definitely smaller than 1 over n, right? And so it is definitely decreasing. It has a limit to infinity of 0. And therefore, through the alternating series test, it is convergent. And if you imagine what's going on here, if you remember, it's 1 over 2 and 1 over 3. Basically, if we take the sum of the first term, that's 1. Then we take the sum of the second terms, that's 1 minus 1/2, which is 1/2. We take the sums of third terms, which I think is 5 over 6, and then 7 over 12. So basically what's going on is 1, then we minus 1/2 to it, so that's 1/2. And then we plus 1 over 3 to 5 over 6, we minus 1 over 4. That's going to keep going like this, and then it converges to this point. That's how the sum to infinity works. In a quick note, just like the other video, just like the other the tests, AST can only tell you the things within its limits. So for example, if the limit to infinity is 0, and if the series sequence is decreasing, then it definitely is convergent. But if the limit isn't 0, or if the series isn't decreasing, it could still be convergent, right? So it doesn't mean that just because it fails those two conditions of AST, it's divergent. No, that's not true. And it could also be convergent in those circumstances as well. We have to do our test to find it out. That's just a quick heads up about those things. Again, this is the same thing with AST. We're just doing some stuff to it, like we're doing the limits, and then we're checking if something's larger than difference. I want to show you a quick trick though. So let's do this. So it's the sum to infinity of n over n squared plus 1. That's the sequence that we really care about. That's Bn. This is Bn. And let's check for infinity. So n over n squared plus 1, that's definitely 0. And then we look at this. So we need to imply that n plus 1 over n plus 1 squared plus 1 is less than n over n squared plus 1. Well, what we can do is we can imply a function from this. So let's do a function. See this? This just goes here, right? So what we have is x over x squared plus 1. And to find if something is decreasing, we look at its derivative. So we derive this. This is a quotient rule. So it's going to be x squared plus 1 minus 2x times x over x squared plus 1 all squared. And when you simplify that, what you get is 1 minus x squared over x squared plus 1 squared. And we know that this is, we know that this is less than 0 because this side is always going to be positive. So we know that x is always going to be larger than 1 as we start from 1, right? So if you imagine all the scenarios, let's say x is equal to 10, which is what I wrote down here. When x equals to 10, this is still a positive number. This is a positive number for all x larger than 1. And then when x is larger than 1 here, it's going to be a negative number. So you have a negative number over a positive number. The final result is a negative, right? If x was equal to 10, it would be minus 99 over some random positive number, and that would be a negative number. And if the derivative is a negative number, it means it's decreasing. And so we therefore know that this is true because it just means that the series itself, the sequence itself is decreasing. And therefore, since both of the conditions apply, this series is converging through the AST. So that's the kind of idea we're working with here. And one final thing, again, I guess this is a really cool example too. So this is the sum to infinity of cos n pi over root n. And if you remember, when n equals 1, cos of pi is going to be equal to minus 1. So it's minus 1 over root n, then root 1. And then the next one is going to be 2 pi. Cos of 2 pi is 1. So it's going to be 1 over root 2 minus 1 over root 3. That's the idea, right? And so we can rewrite it as this to make it seem more easy. And basically, now we just check the limits again. This is actually quite simple. The main idea is just this cos thing that I want to show you. But again, these both work as the condition out. And so they are convergent through the AST. So finally, I want to look through one final idea, which is called estimating AST with an error. Right? We're estimating AST with an error. I'm going to give you an idea. So assume that we have a decreasing sequence, right? That isn't 0. So Bn is larger than Bn plus 1. So it's just 1/2 is larger than minus 1 over 3, minus 1 over 3. Oh my gosh. Minus 1 over 3, then 1/4, that kind of stuff. I think. Yeah. And then where the limit of this is going to be 0 again. So it's it sets it up to be convergent just like the other one. But remember, this is AST, not a normal sequence. Before, with the I think that was the limit test, the comparison limit test. No, that was with the AST. So yes, it is. It's the same two conditions. It's a decreasing series, and the limit to infinity is 0. So now we let the sum, the actual sum, the sum of the whole series. I'm going to name this the actual sum. The actual sum of the whole series, like to infinity, is S. Now, if AST converges, so that's just saying that the conditions are true. It's a convergent series. So all those conditions we say up here are true. What you end up with is if you had a SK, which is a partial sum, and if you had a large enough k, like if you have a very big k, let's say k equals 100, then what you have is an estimate of AST of the actual sum, and then what you have is the actual sum minus the partial sum till k is less than or equal to the next term in the sequence, bk plus 1. And I know this is a bit hard to decipher, so we're going to do an example. But what we're doing here is we're taking the actual sum. Let's say the actual sum is 2, and then our estimate is 1.5, right? Our estimate is 1.5. Then in the sequence, the next term, right? If we had, I'll show you an example, but then it would be less than here, which is less than 0.5. No, it's just next in the next term. So I'll show you an example, but basically you can see how the actual sum minus the estimate sum gives us an error, right? This is an error, right? The actual minus the estimate gives us an error, which must be less than the next term. And I'm going to show you the proof for that, or like the idea for that. So let's say we have the sequence, the series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, right? So if we did k equals 2, and so we did the sum until 2, what we have is 1 minus 1/2. That's the sum until 2, 1, 2. So we have 1 plus minus 1/2, which is 1 minus 1/2, which is going to be 1/2, right? What we're saying is the actual sum of the sequence, the actual sum minus the sum until k, which is 2, is going to be less than the term which is above the 2 that we just did, which is the third term. So what we have here is this actual sum minus the sum until 2, which is 1/2, is less than the third term, which is 1/3. And if you imagine, what we're saying is that whatever the sum is, right, 1/2 here, is going, we can't be any far off. If you imagine that scenario where we're jumping around like here, if we're on this step, we can't be any further off. We can't be any further off than this, right? Like the actual sum, let's use a different color. The actual sum, like if this is 1/2, this is 1, this is 1, after plussing 1/3, right? The actual sum is somewhere between the plus 1/3 and 1/2, right? Like it has to be somewhere here. And so it can't go further than 1/3. And this is the idea, right? That's the idea. You can't go, because this is going to be an even smaller number than 1/3. So you can't, this error we have can't be larger than the next term, which is 1/3. And so let's do a few examples here. So it says estimate S of this, basically the infinite sum of this series with an error of less than 1/100. So let's write out the equation here. We have the actual sum minus the sum until k is less than the error of the next term. Okay, so we need something less than the error of 100. So we need this here. This needs to be equal to less than 1/100, right? That's the kind of idea that we're trying to do. So we're gonna let we're gonna let b k plus 1. We're gonna let b k plus 1 is equal to 1/100, and b k plus 1, because bk is 1/n, it's going to be 1/k plus 1 is equal to 1/100. Therefore, k plus 1 is equal to 100, and therefore, let me just do that. K plus 1 is equal to 100, and therefore k is equal to 99. And we should choose a k that is around 99, so we're going to choose 99. And then you just use the sum of 99. And in class, we did the calculator values, like we just used the calculator to do it. And basically, you see how the sum of 99 is 0.698, and the sum to infinity is the ln of 2, which is 0.6913. So you can see how we're off less than 1/100. The error is less than this, which is the whole idea of the equation. This is another example here. So again, it's the same thing. Sum to infinity of this sequence here, of this one. So it's 1/m squared, because it's -1 and -1, and this is bn, right? This is bn. And so again, it's less than 1/100. So you want to let k plus 1 equals to, like, the k plus 1 term, bk plus 1 must be equal to the error. And so we have 1 over k plus 1 squared is equal to 1 over 100. K plus 1 squared is equal to 100. K plus 1 equals 10. K equals 9. So that's the idea. But yeah, that's it from me guys. Thank you guys so much for watching. Hope you guys have a nice day.